Hello everyone, let's work on this fluid mechanics problem. And this one is about pipe flow. They want us to consider a steady, laminar and fully developed flow through a straight pipe that has a circular cross-section. We can see it right here in these two sketches. There's from the side, this is from the cross-sectional view. And they want us to consider a one-dimensional flow where every molecule of the fluid is heading in the z direction and the flow is symmetrical about this z-axis. In this setup, we're going to deal with a pipe flow. Therefore, we're not going to set it up with the Cartesian coordinates x, y, z. We're going to set it up with the cylindrical coordinates, okay? And here's the Navier-Stokes in cylindrical coordinates and the continuity equation also in cylindrical coordinates. Here, big list of things that we're going to take a look at and trying to figure them out. Okay, let's get started. So, in order to find the first thing they asked us, which is the velocity profile, we're going to have to rely on Navier-Stokes, or otherwise known conservation of momentum. We're also gonna use conservation of mass to help us cross some things out from this large Navier-Stokes equation. Okay, this is the Navier-Stokes equation, right? For cylindrical coordinates, and this is the z component version. Now, as we can tell, we can cross quite a few things out, but let's make sure that we have valid reasons why we can do so, okay? So, first thing, they told us that we are dealing with steady state conditions. That means there's no change with respect to time. And in this entire equation, we can see that only the very first term is dependent on time. Therefore, we can cross it out. Now, let's take a look at Vr, Vtheta, and Vz. These are the three components of our velocity, right? So, they told us that this is a one-dimensional flow and every component of the flow is heading in the z direction, meaning that no molecules in this fluid are heading towards the wall, which would be the r direction, or heading in the theta direction, which would be like this. In the theta direction, imagine that as the fluid is flowing, that would be like the flow would be swirling inside the pipe, right? So we don't have that. Every single component of this flow is heading in the z direction. Therefore, let me take these out. Therefore, we can be confident that Vr equals 0 and Vtheta is also equal 0. Vz, we can't cross out. We just said that everything is going in that direction, so we need to leave that guy alone. Okay, now, but let's take a look at the term that is right next to Vz, the change of Vz with respect to z. So, we can cross this guy out based on the information that we can find from the continuity equation. Here it is. We can write it up in cylindrical coordinates again, just like the Navier-Stokes one, right? And just like we discussed, one-dimensional flow, Vr is 0, therefore these cancel out, and we have a symmetry based around this z-axis. We have azimuthal symmetry, or I hope that's how you say that word. It's quite challenging, I guess, for me, but that's what it is, right? And because of that, the change of the theta, v theta, that would be going around like this, or doesn't matter, we take a point here, 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 wherever, as we would go around, it's symmetric around like that, okay? And because of that, this guy is cancelled, okay? And what we have left is what we've been looking for. There it is. We can come back to the Navier-Stokes and cross it out. Okay. Next up, Fz. this term. These are the body forces, and in cases like this, the only one we will usually take a look at is gravity. And gravity would be pointing straight down here, and therefore the component of gravity that would affect our flow, which is in this direction, is 0. Therefore, we can confidently cross it out that it does not affect our calculation. They told us that the flow is fully developed right here. That means that when it comes to the pressure term, we will have a constant component, right? The constant term. So when we're gonna end up having a differential equation after we canceled all this stuff out, is very good that this guy will be a simple constant. If it would be another differential term, then it would lead us to having a partial differential equation, which will be a lot harder to solve than the ordinary differential equation that we end up because we have this as a constant. Okay, next term, this term stays. There's nothing we don't have any reason based on what we can cross it out. This term we can cross it out because we just said that we are dealing with a 2D flow. Don't get confused. This is a one-dimensional flow where the fluid is flowing, every molecule is flowing in one dimensions, but we are analyzing it in 2 dimensions, right? Z and R, okay? And also, if we think about change of Z with respect to theta, like we described it a minute ago, see the way we would go around the circle, we would not have any change because it's symmetrical around the z-axis, okay? So as we would go around looking with respect to theta, there would be no change. So whichever reason is more easier for you to remember, there it is, and cross it out. Now the last term right here, we can cross it out based on information from the continuity equation because we found this guy right here, and because taking a derivative of something that will give you a 0 and then taking yet another derivative of that 0, well, you will still get yet another 0, right? So therefore this term is gone as well. Okay, there you have it. We crossed out everything that we can cross out, and that's it. All right, let's clean it up. Here it is. I copied and pasted the equation from the other page, and you can see everything we crossed out. So let's write it up. On the left hand side, we crossed out everything. It's 0. On the right hand side equals negative 1 over density times the pressure term plus kinematic viscosity times 1 over r, the change with respect to r, and in parentheses r times change of Vz with respect to r. Now I'm going to go ahead and change the kinematic viscosity into dynamic viscosity based on this guy right here. Okay. Rearrange some terms. I'm going to take these guys to the left hand side. The density times kinematic viscosity. There's the dynamic viscosity now, and this term stays as is for now. And let's see, here we have on the right hand side this derivative, so we can see that we are taking a derivative and we have 2 terms inside this parenthesis. Therefore we're gonna apply the product rule to take care of this derivative. We can see the formula for it right here. Break it up, and the first term, the derivative of r with respect to r, is just simply a 1, and here the derivative with respect to r of another derivative with respect to r of Vz, that simplifies down based on notation as the second derivative of Vz with respect to r. Here it is. It was covering it for a second ago. Now we can see it better. Okay, so let's clean it up. This is what we would get. Now, for the next step, it's kind of hard to foresee of what you should be doing, but let me explain what's happening here. So I'm going to try to manipulate what we have here into a form where I can do the product rule backwards and simplify it down a bit, these terms. So here I multiply it with an r. We have an extra r on the left hand side now, but these terms will allow me to do a product rule backwards, and instead of having these two terms, it'll simplify down into this derivative right here. On the left hand side, still no change. And also we can see that since we're taking a derivative with respect to only one term, we are not dealing, for sure, we know that we are not dealing with a partial differential equation anymore. We know that this is a constant and all derivatives here, it's with respect to r. Therefore, the sign of the partial we can change it into an ordinary regular derivative, so d over dr instead of this kind of sign, right? And rewrite it like this. Now, in order to find the velocity profile, which would be the vz, right, just by itself without all this extra baggage that's over here in front of it, we need to take a derivative of this equation twice. Okay, and we're gonna have to do a little tweak in the middle between the two integrals because there's this extra r here. Okay, so we're gonna have to take an integral twice of both sides. Okay, all right, so let's do the first one. Here it is. On the left hand side, this derivative disappeared and all we have left is r times dvz with respect to dr, and on the right hand side we have this constant r squared plus c1. Now, before I take another integral of both sides, I'm gonna multiply both sides with 1 over r. That will help simplify the left hand side, and then I'll take an integral. Here it is. It's much better looking, and if I take an integral of the left hand side, it'll simply turn into vz over here, which is what we're looking for, right? Our constant r squared plus c1 ln r, because you have to take an integral of this guy too, right? And this is integral of 1 over r will be simply ln r. And then a new constant from the second integration, c2. Now this, what we just found right here, is our general solution for the differential equation that we started with. Okay, very good. But we're gonna need to figure out the particular solution of the differential equation in order for us to have our velocity profile. And in order to do that, we're gonna need to figure out this guy right here, c1, and this guy right here, c2, the two unknowns. In order to do that, we need to rely on our boundary conditions. First one, I'm gonna take a point right here at the center on our axis, right, and our z-axis, r equals 0, and over here we know that the derivative of vz with respect to r is also 0. Now the second location right here at the wall, here we know that r is equal to capital R, that's the distance, right? It's given, it's a constant, we know it, and r is equal to capital R. And here at the wall, because of the no slip condition, we know that vz is equal to 0. Okay, let's use these two boundary conditions. We can plug into the equations that we just found, use them, and we can determine c1 equals 0 and c2 is equal to this constant right here, 1 over 4 dynamic viscosity times the pressure term and times r squared. Now that we determined our two unknowns, let's update our general solution and obtained our particular solution right here, and this will be our velocity profile. Now if we factor out a few common terms, we can see that a more compact version is also possible. So there it is, our velocity profile for Vz. Alright, we took care of the first question. Let's go ahead and knock out a few more things on that big list. So let's find the maximum velocity. Now where does that velocity happen? Well, the maximum velocity will be right here at the tip, right here at this point, right? It's not gonna happen right here at the wall. It's not gonna happen somewhere in the middle. It will be right here at this location where we have the vertex of this parabola that we can see as our velocity profile, right? Right there, the vertex. Here, Vr is equal to 0. So let's take our velocity profile that we have just found in our previous question. We're gonna take this data that we know for sure, plug it in, and we are able to determine that Vz is equal to Vz max is equal to this big pile of constants right here, minus r squared over 4 times dynamic viscosity and times the pressure term. Now let's take a look at the discharge through the pipe. That would be the volume flow rate. It can have units as meters cubed over per second, or maybe feet cubed per second. So how are we going to find that? A formula for volume flow rate would be velocity times area. But this we can use only when the values are constant. Here we know that this V is a function, right? We just found it in the previous question. Therefore, in order to use this formula, we need to use its integral form. And that would be integral of V times a differential element of the area. Now this differential area will break up into 2 pi r times dr. Okay, we are working in cylindrical coordinates, okay, don't forget it. So let's take this one, plug in our V function that we have found earlier, and figure out this integral. Not that complicated. Break it up if you want to in 2 integrals, or just solve it as is. We can take these constants out. Here it is. We can evaluate it from 0 to r, right? Because that's where we're doing the integral. We are going from right here, from the 0 all the way out to the r. That's how our profile changes, right? We can see it here too in the how we can right here, right? This is from going from the center towards the edge, towards the wall. We can see that the curve changes, and that's what we're trying to capture with this integral. That's why we are integrating from 0 to r. Okay, so here it is, our volume flow rate. We can simplify some stuff, and here it is. This is all just terms that we know. These are all constants. Basically, we can consider it known. Now let's take a look at the average velocity. Up here we found our maximum velocity, right? Down here, let's take a look at finding the average velocity. For that, we're gonna take the volumetric flow rate that we just determined up here, and we're gonna divide it by the area. After simplifying out a whole bunch of terms, we can determine right here, negative r squared over 8 dynamic viscosity times the pressure term. Good. Let's move on. The shear stress. They want us to find a function that describes how the shear stress is behaving along in this flow. This is the equation for the shear stress, right? We have dynamic viscosity times the derivative of Vz with respect to R. Now, this derivative term right here, we found it when we were solving the differential equation from the Navier-Stokes. It was one of our equations, the derivative of Vz with respect to R. So we go back there, copy it, and plug it back in here. There you go. Dynamic viscosity will cancel out, and all we have left is 1/2 times the pressure term times R. This is a function of the shear stress with respect to R, right? Because that's what we are expressing it in. Good. And what we have? Maximum shear stress. What do we have? Where do we have maximum shear stress happening? That would be at the wall, right? As the fluid is touching the walls of the pipe, that's where the maximum shear stress happens. So we'll take this equation that we determined right here, replace R with capital R, and we are able to find our maximum shear stress, which is 1/2 times the pressure term times capital R. Good. And our very last term, I guess, what we're trying to find is the friction coefficient. For this, we're simply going to utilize the formula of the shear stress at the wall, right? The shear stress function, which is at the wall. That's why I have this capital R right here. I hope you guys can see that. And divided by 1/2 density times the average velocity squared. Plug stuff in, and after a little algebra, we can figure it out that it's 16 over the Reynolds number. And the Reynolds number, in case you guys forgot, it's right here. Here's the formula for it. Okay, there you go. Hopefully it wasn't too long, but we solved quite a few questions. So have a great day, and please subscribe and like the video.